Well, welcome to section 7.1. Today we are going to introduce ourselves to the exponential function. For the most part, everything that we've looked at this year can be classified as a function, but they've been either trigonometric functions such as sine, cosine, and tan, or they've been polynomial functions such as a line or a parabola or a cubic or a quartic function. Today we look at the variable changing from being kind of the base of the expression to becoming the power or the exponent of the expression, and that's called an exponential function. So you can see in the expression y equals c to the power of x, that x is now in the exponent. And there are two different types of exponential functions we're going to look at, and really they're the same. One is increasing, which is called growth, so that is that function there. And then we have decay, which means as you go from left to right, it gets less and less and less. And all exponential functions, as well as logarithmic functions, which we're going to look at in the next section, have this same basic shape where there's a large growth that happens relatively quickly, and then you can see that the graph is also getting less and less in the opposite direction. So let's go ahead and look at one exponential function and see what we can learn about that, and then we'll go from there to the lesson and to the assignment in class. So we're going to graph the expression y equals 3 to the power of x. And so for us to graph it, I think using a table of values probably makes the most sense. So I'm going to just make a little chart here with x and y values, and we'll see what we get. And 0 is always a logical place to start. So let's go ahead and put x equaling 0 in there. So what is 3 to the power of 0? Anything to the power of 0 is 1. And that's going to be one of our key points on all of our exponential graphs, is that value when x is 0. Let's put 1 in. What's 3 to the power of 1? Well, that's 3. Put 2 in. 3 squared. 3 times 3 is 9. And we could continue on indefinitely. Obviously, the numbers will get large really quickly. We'll go from 27 to 81. So I'm just going to stop there. We also need to consider negative values. What if it's negative 1? Now, 3 to the power of negative 1 is the same as 1 over 3 to the power of plus 1. So in order to evaluate a negative exponent, we need to move the power to the denominator. So that's 1/3, or 0.3 repeating. When we have negative 2, 3 to the power of negative 2 is 1 over 3 squared, which is 1/9. So we'd end up with 1/9. So it's getting smaller. And if we continue on to negative 3, we'd get 1 over 27, so yet a smaller decimal value. And then it gets 1 over 81, 1 over 243. It's really, really small, but you'll notice it will never, ever get to being 0. And it will never, ever be a negative number. So when we go to graph this exponential function, I'll just draw an axis here, x and y. When we go to graph this function, and I start putting the points on, okay, we have, just give me a, I'll use this. We have 0 and 1, which would be right about there. Then we have 1 and 3, which is right there. And then we have 2 and 9. And I can't even put 3 and 27 on my scale because it's gotten too small. So we can see on the right-hand side, this is an exponential growth question, because it's growing as we go from left to right. If we go in the negative direction, negative 1 and 1/3 would be about there. And then 1/9 is a little smaller. And then 1 over 27. And then 1 over 243. And it'll continue to get smaller and smaller and smaller forever, but it will never quite reach the x-axis. It will get infinitely close as x gets infinitely small. So let's talk about domain and range and intercepts. Starting with the domain. This graph goes to the right forever and to the left forever. So it's the set of all numbers x such that x belongs to the real numbers. Goes to the right and left forever. Going to grow as we go to the right and gets less as we go to the left, getting very, very close to 0. The range is a set of all numbers y such that y is going to be greater than 0 and includes all the numbers greater than 0. So there's an imaginary line here, which we have as being the x-axis, which I'm just drawing over with a dotted green line right now. This line right here is a horizontal asymptote because the graph gets infinitely close to it, but it never crosses it. It's an imaginary line that it does not cross. We have no x-intercept. There's no solution to this. There's no root. There's no 0. But there is a y-intercept, and it's at 1. The equation of this horizontal asymptote, just noticing up here that we're supposed to find that, would be the line where x equals 0. That is the answer for that. So what we're going to look at in this section are the shape, the domain, the range, the intercept, so that we can draw an exponential function. But we're also going to look at, well, what's the equation going to be to get this decreasing situation? We just drew the increasing situation, which is in blue there. How do we get the pink, and what determines that? And you can see it's related to the C value, and we're going to look at, well, what happens when that C value changes? And you can see the conditions here are, well, here the C value has to be bigger than 1. Here the C value has to be between 0 and 1, which implies a few things, such as C then can't be 1. Why can't C be 1? And then why can't C be negative? There's no condition here for C being negative. What happens when C is negative? So we'll talk about that as we get into this lesson together. But hopefully this gives you a good idea of what we're going to be looking at. And I don't think this will present us too much difficulty. And I will deal with that when we get to class. So I'll see you soon. Bye-bye.